please. Okay, for people who are joining this live stream, we are talking about control systems and preparation for version 12.3 of Wolfram language. And we're just starting to talk about connecting our control systems capabilities to machine learning and connecting system modeler to control systems and machine learning and so on.
So we're not going to talk about machine learning today.
Okay. We got, so what, where do I start here?
Okay. So the thing, so let me just describe the overall workflow so we understand that. So the typical workflow, one important reason to model something is because you want to control it in when it comes to engineering systems and the like.
Yep.
So the typical workflow that you then do is that you need to build a model in the control context. That model of the thing you control is always called a plant model.
Okay, as opposed to an animal model. Never mind, I'm joking.
Like chemical plant, regardless of whether it's a rocket or what it is. Fine. Okay. There's some things you need to do there, but then the typical workflow is that you're going to linearize that model because you're going to then design a controller using linear design techniques. There are non-linear design techniques, but they're much less mature. And the one that's sort of robust and works well are linear design techniques.
Okay. So in other words, if your plant stays within the linear regime, you're in good shape. If the thing goes non-linear, you're screwed, basically.
Sort of. There's things that happens when you use feedback that tends to keep you in that regime.
I see.
So it works remarkably much better than you think.
Yeah, I get it.
Nevertheless, there are issues that your typical Boeing 737 or whatnot will have several dozen of these in different parts of your flight envelope. Okay, but this makes it easy to go from system modeler, linearize your plant, do your control design, but then it was super complicated to get something back into system modeler because these control functions returned all kinds of different things, special things that you then needed to specially do something with.
Right.
Okay. So there was a lot of do-it-yourself work to try to get. It was all doable.
So wait a minute, just so I'm clear, when you have a controller, like a PID controller or something, can I see what is our version of that? What's it called?
PID?
PID tune.
PID what?
Tune. The second one, yes.
Okay, so this gives a PID controller.
And the way it is connected back is in the details and options. So.
No, but I'm just trying to understand what comes in and what goes out when you have one of these controllers.
A plant model goes in and a controller comes out.
Okay, but wait a second. So this is an example of a PID controller, this thing here.
Yes.
Is that right?
Yes.
Okay, so if I take that thing and I just say, okay, so I take this, and now what do I do with this? What can I do with this?
Yes. So earlier, you had to use the function systems model feedback connect to connect it back to the plant, and that's the.
I want to connect to the plant. I just want to see the thing. I'm much more clueless than that.
Yeah. So the controller doesn't work by itself. It has to be joined together with the plant.
If you open the detail section, Stephen, you can see conceptually what the heck goes on. See the GFB there? That's the controller.
Okay, but I mean, if I were thinking about this like a layer in a neural net or some such other thing, I've got an E of T coming in and a U of T coming out. So how would I actually, given this object, how do I feed in an E of T?
Oh, you would do output response. So you'd use output response and give the ET signal. Whatever.
Okay, so what could my signal be? Sine T or something?
Yeah, sine T.
And then do I go comma T or something like that?
Yeah, you can give comma T. It will try to do it symbolically or, yeah.
Okay. And so what this means is, I'm just trying to understand what this means. This means you have this controller, you're wiggling the input to this thing, and this is the output it's producing. Is that correct?
Yeah, if that is the input, this is the output. But we are actually wiggling R of t. The one before that, yes. And then
I understand, where there's some feedback loop here.
Mm-hmm.
Exactly. So what you want to do is to change the user interface to that system, to that plant. Do you see what I'm saying? So normally, if the input would have gone directly into the else's thing, now the input is the RT that goes into the controller connected to your system.
Okay.
See what I'm saying? So
I don't really see what you're saying. What is LSYS?
That's the plant model. That's the thing that was that you used to design the PID controller.
Oh, that's linear system. LSYS
Yeah.
means linear system.
Yes.
Okay. Okay.
So that's the original system, the plant model. Now we're going to think of this sort of hooked up like it is here with a controller. Those other signals, DT, MT, and so on, those are disturbances that act on your system. So for instance, if it's a cruise controller for your car, that could be a hill that's not modeled. That could be wind.
Okay.
Okay. And the goal for the controller is to cancel out those disturbances that are not modeled. So that even if there's a hill going up, you still keep it at 60 miles an hour.
See, that's a very good example. So when we are doing manual speed control, the input to the system is the gas pedal. But when we are doing cruise control, the input to the system is the speed we set.
Yeah, the set point, you know, exactly.
Okay. Okay, I understand. All right. Okay, so now, I get the basic setup. So now what is new here?
So what's new is that we've provided, so this PID tune had a really good idea in it that we basically generalized to all control systems, which is that it can give you a data object out from which you can get all the possible transfer functions that you might want to get.
So how do you get the data object from PID tune?
Yeah, that's the last. Yeah, we have to give. That's in. If you look at scope, probably that's an example there. But you have to give another argument to give for. Go to properties. Yeah, there's that example, PID data, and it'll give you that data object, which we have now generalized to systems model controller data, and plan to make PID data obsolete.
Hold on.
So what this one gives you is access to many more things in that graph.
So why isn't this just information?
What information?
Well, the function information.
There's nothing more there. It is what you see.
No, I understand that. How do I get what I'm supposed to be getting from here?
Oh, you get it from PID tune. If you evaluate PID tune, if you evaluate that, you'll now get that systems model controller data if you are in the prototype build. Just evaluate that example.
This one here?
Not this one, where you had the PID data input. Yeah, then this
but I thought you told me that the PID data was about to be obsoleted.
Yeah, but it'll still work. So just
no, but I don't want to see what the past. I want to see the future.
Then go to PID tune new.
Yeah, it'll give you the future right now because it's backward compatible. That's what I meant. That's why I mentioned. Yeah, this page is just it's just the same as that. Yeah.
So I don't understand. What is the proposed design?
The proposed design is to allow returning this systems model control data is what allows us to give a clean workflow.
Is that what this is doing?
That control.
This is
no. This is an easy use case that just gives the raw data back.
Where's
the use case where you're giving back the fancy thing?
Yeah. So just yes, that example is right here. So if you copy that what you had before, yeah, copy that and evaluate it. Because instead of PID data, we'll obsolete that, and now people will just give systems model controller data.
Where do they give that?
Instead of PID data.
Oh, why? So this giant long thing.
Yeah, that we support PID data for back.
No, but why is it not just called data or something? Why does it need to be systems model whatever? Because
it's a system symbol now.
I don't understand. This is a string.
Yeah, the input there.
Okay.
There's nothing to do with this.
Yeah, I mean, the string could be shorter. Is that what you mean?
Yes, that's what I mean.
Okay. Sure.
Systems model controller data.
That's the head for that template. I mean, the output.
I see. And why is it exactly that this thing here, that if I say information of that thing there, that I can't get something like this out?
There is only the transfer function.
I see. So it's only, I see. So this is the one which has everything.
Yes.
Okay.
And one of those.
Okay. So what I'm saying here, let's see, what do you want to do here? You want to say, so the default is still to just produce a transfer function. Is that correct?
Yeah. It's kind of like getting immediate data out, but it's not everything you need, depending on your workflow.
Right. But so what I'm thinking is, I don't know whether data is the right term, but systems model controller data. I mean, in a sense, make more sense to at least just call it that, I would think.
I agree. I think that's a better name.
Okay. Okay, fine. All right. So so you've got this thing out. Now what?
Yep. Now I can wire that up.
Now with that, we can ask all kinds of properties. Now you can ask for that original controller using the name of that controller is feedback.
Okay, so I can say %3 sub. Is there a data set here?
Yes, property data set.
Why is it not listed in the list of properties here?
Or should be, it's called property data set.
But that's wrong. It should be called data set because that's what it is for everything.
Oh, okay. The ones.
And I don't even see property data set here unless I'm not spelling it correctly.
No, it's okay. I think I missed that correct design because one of the functions I looked.
What function did you look at?
I forget which one, but I designed my functions like this with property data set and property association.
That's not right. I think it should be. I mean, the way it works for entities, at least it's just data set.
Okay, I looked at something else and had this like this property data set and okay, I'll correct
it. All right. Okay, so this is. I don't understand what these things mean, but this is.
Yes. So all these refer to different aspects in that details and section in that block diagram.
Okay. And where can I get the block diagram? Is there a block diagram version that I could see here?
Yeah, the block diagram is right now just in the details and options.
No, there isn't one.
There isn't.
Well, so I'm asking, like for neural nets, we went to a lot of trouble to actually have it be the case that
we don't have that for control. Okay. We never designed that.
Would it be a good idea?
Yes, it is a good idea to actually see it. Yeah, but it's some work too.
But I mean, so roughly what you're saying is, in one of these systems, you can describe one of these systems symbolically in the control system framework, right?
Yes.
I see. And so then there's a question of that symbolic description right now just has some textual thing like this, right?
But when the one thing to remember, the original work done on control systems, it never preserved the structure. It never preserved the graph structure. It always reduced to a new canonical form. So it was always gone.
I see.
That's what I'm saying. They were just all
I get it.
Flattened out.
Yep.
But now it's not.
Right.
When you use systems model controller data.
Yes. And then if you ask.
But if you use PID directly, then it will flatten it, right?
Yes. When you ask PID directly, it just returns one of those properties in that data object.
I get it. Why is it called systems model controller data as opposed to systems model controller? I guess
Because
it's the data.
it's more than the controller.
Yeah, the controller is just one property.
And should it be called controller data or controller information? Based on our other use of the term information.
I mean, historically, we called all these things data.
Because it was PID data.
No, but also in all kinds
data?
of other areas, we've called them all.
PID data is the legacy function. Yeah.
Okay. All right. Okay. Okay.
So there's a lot of things that you want to find out. For instance, how powerful is my systems in its ability to reject disturbances? Like, yes. How big of a hill can you hit with your car before it starts, and it still keeps the speed up?
Yep.
It's like good to know.
Yes. So.
Yeah. So all of those things are available in that object. That's another transfer function that goes from, that tells you, basically how much those things are.
So what are these here? This is estimator, regulator. So these are all functions.
Yeah, you should look at the new ones. Yeah.
You have to look at the new pages.
I know.
These are old functions that have been upgraded with this ability.
To do what? To generate the property, by the way.
Yeah.
To generate the property, and now it also directly supports system model, from system modeler. So now we automatically.
Okay, that's a different thing that you're describing here. So if what you're telling me is that if I do this instead of controller data, why is it spinning my disk? Why is it? What is there something dynamic here? What's going on?
No, there's nothing dynamic there.
Well, there's something wrong because it was spinning. It was doing a not ready type spinning thing here for the formatting of this, which seems very suspicious. Okay, so you're saying if I say system model here.
No. If you give the system model as the first argument, if there's a system model object as the first argument.
Okay, so let me get a system model object.
Go to connect system model controller, and there you'll get examples that work. Because otherwise, normally any model, most models are not controllable. Think about it yourself. You're modeling a system. You don't want any unknown input to it. You want it to be able to be simulated as is.
Yes. But so there has to be some stochastic input.
Yeah, or controllable input. Like if you have an inverted pendulum, what is it that you can control? What is it that you can affect?
Right.
We have to point that out. So here's a simple engine, it's like a DC motor.
Okay. So if I now say system model, just so I'm understanding, why is this called systems model? I don't understand. That should be system model controller data, but we're taking off the systems model anyway. But why was it systems plural model? Do you understand my question?
Yeah, it goes back to the naming differences between control and system model.
Okay, but it's wrong, right? So let's elide it by just saying controller data. Is there anywhere else where you're using systems plural model?
Yes.
Okay.
All the control system functions is systems model.
Where?
The ones that were designed for version 7 and 8. And
no, but what are they called?
They're all like systems model, series connect, systems model, parallel connect.
Okay, but are they? Boy, that's a mess. Okay, so if I say control systems.
If you look in model connections.
Okay, so we've got a mess here. We've got a mess. How do these relate to the system model, the modern system model things? Do you understand my question? Are they compatible or not?
So they're not. They work on transfer functions and state space models.
Oh my God.
but they can be injected into a system modeler.
Yeah, like a subset of what
This is
system
one
model.
way to create models is to create from this class of models. So these are like special models. Special
I
classes.
understand. But then, okay, so I understand here. Okay, so we've got our DC motor.
Mhm.
Okay, so now we've got a singular system model linearize.
Yeah.
Oh, come on. This is crazy. This is crazy. What's this? What's this? What's this about? That's just a bug, right?
Yeah.
No,
That's not
No, it's
intended.
a bug. It shouldn't be there. It shouldn't be a context function. That was because, well, it won't be there in the future, but that's the way they're developing it. So it has to do with branches and prototype.
Okay. All right, I understand. Not a problem. All right. So now, okay, so let's look at this. So this is now taking this model and linearizing it. So for example, could I plot the unlinearized model? Wow, okay. By the way, that progress dialog does not follow the modern standard.
No, it will be updated for 13.
Okay. Okay, so could I, for example, plot, if I do system model plot
Yes.
of %8, what the heck is this? What's that weird stuff? What is that? What's that? What is that?
So in 12.2, captions were introduced in System Modeler.
And I'm sorry, in which?
In 12.2, in version 12.2.
That was never reviewed. That was never reviewed, and they're wrong. What the heck are you doing here? Okay, that's just wrong, right? What is it doing in some weird Courier font? What is it doing? When do we have captions in graphics? This is a plot. It does not have captions.
Right.
What happened here? How did this not get reviewed?
Yeah, we'll take a look at that.
Get rid of it for 12.3, please.
Yeah.
Get rid of it.
It was done for System Modeler, the product, but somehow it snuck in here, and it shouldn't have snuck in here.
Okay. It's rather upsetting. I hope that isn't the case with all system model plots that they've got this garbage in them.
No. Very few have captions.
Well, let's get rid of them. Get it correctly designed. Okay. I'm a little surprised that this is just flatlining. There's nothing.
Right. So the input, it's like you're not giving it any input to the system. So it's just flat.
But isn't the default to have these examples have input?
Well, in this particular case, we definitely want, because with the controller, we want to add stuff. We don't want the system to have sources.
So there are two modes of thinking about this, Stephen. So when you build a model that sort of is complete, it models everything, then there is no such thing as
what just
input.
happened here? What happened here? I thought this was a linearized version of this system. Why can't I plot
it? Well, system model plot doesn't process.
I understand, but that's wrong. Okay, why doesn't it process those things? It's supposed to be a system model. I just said linearize my system model. Why isn't
you got a transfer function? I mean, you got a state space model back, which is not a system model.
Okay, but that's you know that because you're involved in implementing it. Nobody else knows that. So this function better start working on things like these transfer functions, which it can do, right?
Yes, all it need, we can just create system model around it and it'll work.
Great. So if I just say this here.
Yeah, I think you also have to indicate what to plot.
Oh, okay.
Because that's going to create a model, but then now you have to
indicate. Okay, all right. So you guys will figure this out. But the end result should be that these things interoperate.
Right? That's what we're aiming for. But this wasn't one we focus on now. We'll focus on that one also.
Okay.
But I need to explain one thing to you just before we get too far off in a tangent here. If you think of a system as a completely modeled, then the only thing that you set is typically initial values.
Yes.
Okay, that's not the case when you have control, because you have effectively an unknown input function, and you have to specify it.
An unknown intermediate input function, as in,
Yeah.
Okay.
Yeah. So often people, what they do for these systems that are controlled, that have control input, they say, so how does it react if I send it a step? How does it react if I send it a ramp or a sinusoid or something? So you see how it responds to different kinds of input. A step response is sort of like the simplest, that people often look at.
Okay. So how do I do that in this case? For my electric motor, how do I send it a step?
So you have to say input.
Where?
I think it's down there. If you go to the right, you can copy system
input
model.
Here.
Yeah.
Okay. So here, what's the 3? Number of seconds or something?
Yes.
Okay. So if I say this and I say model here, oops, actually, I don't want simulate. I want plot.
Oh, we really have to get rid of those. God.
It's a screw up, but these things happen. But it shouldn't be allowed to happen. Right. Okay. In any case, all right, fine, great, that's nice. Okay, why does that? I don't understand what that's
a pure function.
Function.
It's a pure function.
So I could say hash 3 ampersand.
Yeah. Yeah, exactly.
Nice. Okay. All right, good. Okay, I think I understand that. Now what? Now let's do this grand thing. Okay, so this is the controller.
Mm-hmm.
Now, okay, I see. But it's a controller, it's not controller data. As opposed to commander data or anything like that.
So when you then, the next command, what it will do is to wire it up.
I understand that. I understand it. But what I'm saying, the point that I'm making is, the thing you get out here is a controller.
No, it's lots of things.
No.
It's lots of things. One of them is the controller.
But I mean, that's like saying a classifier is lots of things. You can get, okay, let's review what we've done for machine learning. Okay, you get out a classifier, which can be just applied to data. Or you can say information of that classifier, comma, a property. That's how you get out properties. So there's,
but this one can't be applied to anything meaningfully.
Okay, except that it can be fed into something in the thing that you're about to do here.
Yeah, it can be wired up to the thing it was designed to work with.
Which means it's not really the data, it's really the controller itself that's being wired up.
That's right.
Okay, so let's see what this wiring does. So progress monitor will be nice here. Oh boy. Okay. Where is the controller here? Okay, so let me try to understand. I mean, this is my original, right? The DC motor.
Mm-hmm.
Correct?
Yes.
Okay. So let's see. Can I even see the motor? I don't understand anything here. And by the way, why are these plots fuzzy? Why are these things looking fuzzy? Are they not vector graphics? Are they vector graphics?
I don't think so.
You do or do not?
I think they're rasterized.
Okay, that's not going to work. They should be vector graphics, right? Why are they not vector graphics? They're clearly very vectorized kinds of things.
I don't think we could answer that very easily, right away.
Okay, all right, fine. Okay, so what is this and what's its relationship to that?
Yeah, okay, I can, because the out 17 doesn't come out really well, but what you're seeing there is that box, that block in the bottom, that is the controller. And that circle that you're seeing on the left, that is where the DC motor is.
Okay, I'm sorry, I don't get this. I added a controller somehow I connected a controller. So I've got this model here, right?
Yes. Mm-hmm.
And I've got this. How do I make a picture of the controller? Is
Yeah. So to see a clean picture, we can see that in the documentation for state feedback gains new. So that is getting a little mangled up when it's coming in that picture in out 17. See that first illustration. So there are three components. One is that DC motor, which is sys. The other one is the controller. And then the third one is the block that is comparing the two signals.
Okay, so they need icons. And this thing here, which is an elided version of that whole thing, which apparently is in unnamed models and a weird UUID. I don't understand what's going on here. This is a DC motor and it's labeled, right?
Yes.
Mm-hmm.
Okay, so why is that not a subpart of this diagram here?
Yes. Yeah. These class of controllers are called state feedback controllers. And over here, we have to modify that model a little bit. If you look at that diagram on the left, we had to pull out those states from inside. So that's why we don't see the DC motor like that.
Sorry, what diagram on the left? I mean, I don't understand.
On the right, sorry. On the right, there is the state feedback gains new. You see that X, we are pulling it out from inside sys. So that's why that the DC motor is not replicated there. We have to create another model. But in general,
I'm very confused. Why don't you just show a picture of this? I will be a lot less confused if they showed a picture of this, even if it's just a thumbnail, basically, showing that you're pulling this out of it. Do you understand what I'm saying?
Yeah.
I mean, I don't understand what you. This is totally confusing. I mean, this is the input here is a solid arrow, and the output is a non-solid arrow. Here it seems to be the other way around, etc.
Yeah, this one needs some work. But
what's going on here? Look at this. This is totally fuzzy. I don't understand what this is. Okay, what does this picture? This picture should have the DC motor in it there, together with a couple of additional components.
Two more.
One of which includes something with an icon that looks like this, presumably. Right?
So in that icon, you see three things. And on the figure on the right, in that ref page also, you see three things. That are the three things you see in out 17.
Okay, so this icon here is indicating that what this is the blue thing in this diagram. Is that correct?
No.
Yes. This is the controller. You just explained this to me. This thing here is the controller. It's the K here, or kappa, or whatever it is.
Yeah, it is the K there, yes.
Yes, okay, so listen to what I'm saying to you, okay? You are indicating with this icon that this is representing a controller. True or not true?
It's representing a controller together with the plant.
No, it's not. This thing here, this controller data, is representing the data for the controller. You got it from, well, maybe it is. I don't know, actually. Okay, yeah, so you got it from the linearized, okay. You got it from this linearized thing. But this component that's being represented here, that's then going to be connected in, is this thing is a controller. That's what this is supposed to be giving. Is that not correct?
I think I don't quite.
Okay, let's go through it again. Okay. What you've got here. Okay.
It is, but it contains the following additional things. It actually also includes the plant model that you gave as input.
I understand. It contains the linearized plant model.
Yes.
Because it needs that. Because otherwise it can't work.
Exactly.
That is what a controller, okay, there is the framework for a controller, and there is the actual controller for a particular system. Is that correct?
Yeah. Yes. But it uses that to know where to connect it up. When connect system model controller goes to work, it looks it up in there, and that's why it can work in this one-step thing. Otherwise, you would have half a page of code here wiring it up.
Okay, I understand. So there's some ports that basically were transferred through from the original. So we've got the original system model somewhere up here. Okay. This original system model has certain ports.
Yes.
How would I see those ports?
You can. That's one of the properties of it.
Yeah, input variables, and so it's a property called input variables.
And output variables and so on.
But there's no display of the ports. There's nothing here.
No.
I mean, to me, it would be nice if there was a plus sign, for example, that would kind of show me a data set that would interactively go from this diagram, much like in the neural net case, we have that pretty nice click to drill down type mechanism.
Yeah, actually, that's not a bad idea to gradually build out more of that stuff.
Right. But so then, okay, so if we had click to drill down, one of the things you would see is the list of variables.
I mean, we have a full-blown modeling system. So this is, I mean, Mathematica is sort of a junior, it's not a full, we're not going to build another modeling system.
Indeed. But I mean, given that you're giving people the ability to symbolically hook things up, I think you kind of need to tell them.
Yeah, I think it's a pretty good idea, actually. So.
Okay. All right.
Sergio,
okay.
do you take notes? Sergio, take notes.
Yeah, I'm taking notes.
I think it's a good one.
Okay. Okay. So then,
Input
what is it called?
Input variables.
Why is there no autocompletion here? Oh, it doesn't know what it is. Okay. Okay. Does it show me at all where that is? Well, okay, that would be part of this interactive build out. Okay, so that's the input variable. So that's wait a minute. How is the wiring up going to be done?
Yeah. Oh, so this model is very simple. There's only one input variable, and that's the input variable you see in Lin, the V, and that. Yeah. So I can show you in the figure on the right on the ref page.
Okay, hold on. Here we are showing the input variable.
Yeah, that is the. Yeah.
Although here we're not showing the input variable.
But you don't always have input variables. When you build, as I said, when you model something and it's supposed to model everything,
yeah,
usually the only thing you have is initial values.
I understand. When it's a sub piece of the universe, a subsystem, then it'll have input variables.
Right. If it's something you're going to be able to control, then you need that.
Okay. Okay. So now this hookup produced a system here that has a UUID, which is kind of grotesque, and I don't even think you should label it, given that it's a UUID. Why would you want to put that label
there? Well, right now we require models to have names in System Modeler.
But you don't have to display it.
Okay.
That's true.
Yeah, I wouldn't display it. Okay, I'm totally confused here. Okay, I thought you had all the information from the original system, which had been linearized.
But you still need to send. I mean, look at the example where you took.
No, but I can do system model plot on the original model, right?
Well, you can do it on that one too if you specify the input. Let's go down.
But I can just do system model plot without specifying the input.
Right, that's because the original model had store plots. So this new created model.
Why not? Why doesn't it?
We can add plots, yes. Yeah.
Okay.
Oh, okay. So we had added default plots, right? I can look at. We had added some default plots.
Something went wrong here.
Yes, there are default plots that should show up. We added them.
Something went wrong. Okay. Okay.
Oh, maybe it's just you just have to add time, simulation time. If you just add like comma 10, maybe that's enough. No, yeah, no, okay, we have to fix that. Yeah.
There are default plots, but okay, I can look into that.
Okay, fine. Something went wrong. Not a big deal. Okay. So let me just walk through this again. So the big point here is that you have connect system model controller.
This relies on, if we didn't have all that information in what you have in system model controller data, this would have relied on you manually knowing the topology of what to connect.
I get it. I get it. I mean, so my question is, I'm thinking about the name of this function.
Okay.
The parallel one to this is connect system model components, and from there we have connect system model controller.
Okay. Okay. So let's see, how does this work?
In a way, it's close to net graph, in which you have to specify all the pieces and connections independently.
Right. Why is that model brace model comma 5? Why isn't that a 5? What does that 5 mean there? In the system model plot here.
Oh, that's not necessary anymore. Yeah,
Okay, but what would it mean?
We used to have to put that parenthesis there in order to simulate first and then plot, but now it's not necessary anymore.
Okay, so you can change this example, right?
Mm-hmm. Yeah.
Okay. Okay, so system model controller. Okay. Okay. So would I be able to like hook up, this to like the Arduino stuff and things and download some controller to my
Yeah. So there's two interesting scenarios to go there. One is that we have the microcontroller kit, and the controller you designed will work excellently on an Arduino. It will just work right away.
Mm-hmm.
The second thing is that we have also Arduino hook up to system modeler. And that can also work. So you can have it hooked up there.
What's the point of hooking it up there? I don't understand that one.
It's not as much of a point as except that it's a nice modeling environment.
I see.
And it's super popular among people. People download. We have a library for that, and people get it and download it all the time, a lot.
Okay. So, okay. Some more questions. How does this relate to machine learning and particularly reinforcement learning stuff?
So reinforcement learning is sort of, I don't fully understand reinforcement learning, but I intend to get myself up to speed of what works and what doesn't there now. But reinforcement learning is sort of a way a way of doing control.
Yeah.
But it's not clear what works there and what doesn't work right now. The examples that I've seen are sort of very toy, like inverted pendulum. And that's right. What you do on day one in your first control theory 101. So it's not that impressive at that stuff.
No, but I understand. But I mean, if you wanted to insert this stuff, so we've got a way, if I'm not mistaken, to insert a system model in our reinforcement learning loop. Is that true?
Don't know about that. I thought it was the other way around. I mean, we've talked about that, but I don't know that we have that in the ML side.
Fine. Okay, fine. But that's one goal, is to be able to learn to use it as a what am I saying? As a thing that you're learning about, so to speak.
Yeah, absolutely. That's one goal. But I don't think our reinforcement learning has proceeded that far yet. And also, one of the things that seem to have gone a lot farther is sort of gameplay rather than control. Yeah. It's not totally dissimilar, but apparently dissimilar enough.
What do you mean game? Oh, you mean right. I mean, so this is the case. So there are several different frameworks here. So I mean, we have this thing with the the OpenAI Gym, for example, using that in the reinforcement learning loop.
Right.
So I don't know what tentacles that thing has that connect it to machine learning, but it would be good if they were compatible. Now, another thing that we have coming is this virtual machine framework, which is very much a digital devices framework. This is obviously an analog devices framework mostly. That's another thing to point out. Another question would be, what about that game theory stuff that we were discussing? Yeah, there's mention here on our live stream about that. What is the relationship between these kinds of control things and the game theory stuff?
Yeah. So in a way, when you design a controller, you could say that you play a game against an adversary, which is like wind and these things that are called noises that act on the system.
Mm-hmm.
And the controller has this goal, let's say, of keeping your speed constant, regardless of what your adversary, like the wind and the hills on the
I understand.
road.
The controller represents a strategy in the game theory sense.
Yeah.
And so the question is only a plumbing question of, can we insert one of these controllers? I mean, we have to design it.
I don't think it's what we're looking at in game theory right now, but I intend to clarify that a little bit more.
Okay,
but that's
fine.
not what we're aiming for in the first round. It's a little bit, there's matrix games basically and stuff.
Comment from 4D on the live stream. Do these play nicely with stochastic differential equations?
And
for example, our random process stuff.
Not super well. That's gonna so they're both stochastic processes. The way that these control systems are defined, they are sort of a specialized stochastic process in the sense that we think of as the linear systems with Gaussian noise. So, and the controllers that you design are optimal. Given that model of the world, they are the best you can do given that horizon. So they're called linear quadratic Gaussian.
Mm-hmm. So, for example, let's say you have a boat, and I think the spectrum of waves, water waves, is like, what is this? This Pearson-Moscovic spectrum or something.
Yeah.
It's some spectrum of bumping up and down in the ocean.
Yeah.
Which presumably we can get from our random process subsystem, right?
Probably, yes.
Can we feed that into
no, the control systems doesn't deal with sort of more exotic models of random processes.
Okay, only quadratic, only stochastic, only Gaussian models.
Yes,
pretty much. The minute you go to more advanced models, you get into this kind of optimal control that gets very untractable very quickly. So the curse of dimensionality is killing you usually.
What is it? Just for my understanding, Ito calculus, is that all Gaussian?
No, Ito calculus is Ito calculus is what let's put it. It's the differentiation rules that you have to use for stochastic differential equations.
Mm-hmm. By the way, so just so I understand, in the case where you're loading this to an Arduino, for example, so if I take
microcontroller kit. Yeah. So what we would do is we would look at that that data object and ask for.
I can't even find where is microcontroller kit.
You have to search for micro. Well, why
I understand. So this is a bug. This is a bug.
Here's something microcontroller is coming up down there.
Yes, uploading program. Yeah, but they're not the main ones. Yes,
they're not the main ones. No. There is the microcontroller kit guide.
Really amazing. Okay. But so now which of these functions? So I could take microcontroller embed code. So if I took this controller, wherever it is, where is it? This is %16 is a controller. Okay, so now I can say microcontroller code data. Do I need to say needs microcontroller kit?
Yes.
Okay, so now I can say microcontroller code data.
No, embed code.
Okay. Oh, %21.
So you need to pick out the actual controller.
We need to pick out the actual controller and then also say to which pins of the microcontroller we need to connect those.
Why exactly is this thing, if it needs between 2 and 4 arguments, why isn't it giving a red caret there?
Okay, I'll look into that.
Okay, so what do I give here anyway? So I give a target here?
Yes.
Okay. And you think I can use those?
Yes, you can. Yeah. The first argument needs to be modified too.
How?
Yeah.
Because
you need to get out the controller.
Feedback gains model, that's the
Because
controller.
that object contains lots of things, and you only
Okay,
want.
but so this should actually just work, right?
Probably.
Microcontroller embed code should pull out the thing it needs. What do you need? What do I need to pull out here?
Feedback
right now?
gains model. Oh yeah, we have to discretize that model too because this is in continuous time.
Okay, but so all of that stuff should just happen, right?
No, when we design the microcontroller, we also have to specify what sampling we want. All
right, but
how
so
fast?
it should pick a default and give a message saying it picked such and such default if it needed to do it. How do I do that? How do I do the discretization?
To discrete time model. Yeah, and then comma and give us maybe 0.1.
This is not a standard. Oh gosh, why is that yet another non-standard?
Yeah, so this is one way I have to get to.
Okay, well, that's super cool. So now
those progress dialogues are just getting finished. They can't be used until they're finished.
Okay, all right. How do I actually see the code here?
Source code. Property from that is source code.
This is pretty impressive. It was a very simple controller. How could it be so simple?
Because it's just 2 gains.
Okay. That's lovely.
Now, the other thing that you want to do is why you want to inject it back to System Modeler. Now, the example that you took was a particularly simple model, so it's actually linear to begin with. But normally, what you want to simulate it and see where the limits are. So you kind of want to do a lot of simulation work. We're going to work on more functions that makes that much more streamlined going forward. It can be all done today, but it can be more streamlined.
Yes. Yeah, so the typical workflow is before going to microcontroller embed code, we would take that and go back to system modeler if it's a nonlinear model and then simulate it and see if our controller is good. And after some iterations, then choose a sampling period and come to microcontroller.
This is nice. I mean, this stuff all has a certain degree of complexity, and that I don't know to what extent you're giving people workflows where they can just fill in the different steps. Presumably, you've got a bunch of sample notebooks and so on that show all the sequence of steps that are needed, right?
Yeah, and workflows written. We're writing workflow, literally workflows.
So we need to wrap here in a moment, but on our live stream, Fordy is commenting that one thing to point out is that when you link machine learning to process control, is that you can't extract the physics of a well-controlled system because obviously you're living in the regime where little of the physics is visible, right?
What?
If you have a well-controlled system, right, you're living in that domain where the thing is linear in its responses, and presumably that there are, I mean, it's an interesting question whether
I don't know. I mean, so here's how you actually do it. When you're trying to figure out the sort of a plant model, either you model it from raw physics like System Modeler. Secondly, is that you can maybe use black box models, and the neural networks is an example of a black box model, but typically more easier ones. The way you then do that is that you send a bunch of signals to the system and let it respond.
Yeah.
Okay. And that whole discipline is called system identification.
Right.
It's a whole big field in its own right.
Yep.
It's very well developed.
Yep. Fair enough. Okay. Well, good. This is all. This looks it's very impressive and large system here. I mean, okay. This business about systems model versus system model, you know, that needs to get figured out.
Right. Our plan is to gradually, smooth out all of these workflows and build towards higher and higher level functionality and higher levels of automation, which means that it would be accessible to more and more people, including you, Stephen.
Yes, well, that will be good. I've never used this stuff.
Right.
I'm looking forward to using it. I was going to use it on some whole HVAC system, but I don't think it ever happened that way. Wait a minute. Is the RISC-V architecture included in the compiler options here?
No. RISC-V It could be in the future, but the microcontroller kit is compiling to microcontrollers. Each one of those provide the ones that we support provide basically the compiler stack. RISC-V is not yet, I mean, it's getting there, but it's not yet at that sort of stage of heavily used. But I think it has a very good chance of getting there. And there's no reason why we couldn't add RISC-V in the future to microcontroller kit when they're supported.
Fair enough. Okay, we should wrap it up here. Good stuff. And for those who are following live streams, we collided with another live stream. So we'll be a few minutes here, and then we will be talking about discrete computation part 2, right? And Roger, I think you're in that one as well.
Yep.
Okay, so see